So I'm going to look at another conchoid curve, the conchoid of a circle, and this ends up being a well-known curve, the Pascal's Limacon. Here's the mechanism we'll be using. It's a fairly straightforward looking mechanism. The crank and the slider. So let me draw my pole. The slider goes through the pole. We'll make the pole sit at the origin. And let's give it a line coming through here. And the crank going to sit out here. We'll make the crank length A and make that the same length as from A to B. And we'll drive the whole thing by an angle. There at the origin, and the points that are going to trace out our curves, we'll make one beyond C and one the other side of C, and we'll make them the same distance from C. So make that distance B, and make that distance also B. And so now I can get my curve. Let's look at D as theta varies. Now that's an odd looking curve. It doesn't look like any of the ones that were drawn in my drawing. Let's just see what happens as we move theta. See, as theta moves, this is looking like it's doing the right thing. But now we've got a problem. Our mechanism sort of got stuck, and point D is just sort of going round in a circle, semicircle, and then our mechanism gets unstuck. So it's unstuck from 4.6 or presumably 3 pi by 2 between there and pi by 2, 1.57 somewhat. So we really would like this to be going not from 0 to 2 pi, but from minus 1.57, minus pi by 2, to 1.57. That gives us the part of the curve that looks like it's doing the right thing. Well, it is really modeling the mechanism. The mechanism could do that if it can hit a blockage there. Let's have a look at the other point, E, and see what that gives us in the way of a curve. Now I've got 2 points selected, so my locus tool is not available. 1 point selected, my locus tool is available, and I get another curve, which follows on nicely from that previous one. Okay, this looks like one of the curves in my drawing, and we can vary its shape by varying the parameter B. In fact, we'll see there's a special. Well, let's look at the special point in a second. Let's look at the generic version of the curve. Let's have this coordinates is not what I want. Equation. The equation of this curve. Well, remember, this is the first of the curves. This is where D traces. Let's have a look. It's a 4th order, x to the 4th, y to the 4th. So x cubed, x1 squared, y squared. And it looks like it's going to have a special form if 4a squared minus b squared is 0. And that would be b equals to a. I'll have to look for that in a second. But at the moment, let's have a look at the other part of the curve equation. This other part. Now remember, this is now f is tracing out, and we see it is a fact there are two parts of the same curve. We can see they have the same implicit equation. Okay, what if we look for that special occasion where this thing goes to 0? That means we'd have no x squared term. So let's look at that. That means we want b to be equal to 2a. So let's just look at it numerically. Let's make a equal to, say, 4. And b, we can push b up very close to 8, but we could make it 8 exactly. And we see it's got that rather special form of the curve. If we now push b up to something larger, so 10, the curve looks like that. Now, yeah, I'll just do one final step. Let's create an app from this. So if I just long press off with space, I can save an app, and it'll go into my downloads slot. But Google's sitting there, Chrome is sitting there wanting to display it for us, and we can do that. So there is my downloaded app. I can watch, I can move theta, watch the app do its thing. I can also alter the parameter b and see the various different forms of that curve.